We have seen how to define arrays in NumPy. Now we look at a useful type of array, which is a table in a package called Pandas. So why Pandas? Not because of cute furry animals, but because it stands for Python and data analysis. And this is a package which is built on top of NumPy. So it uses NumPy arrays, but it makes it more convenient to use for data analysis. So what do we have in NumPy? We have homogeneous n-dimensional arrays. Data science typically works with tables. So Pandas has two fundamental data structures, a one-dimensional table or a column called a series, and a two-dimensional table called a data frame. The main difference between these tables and NumPy arrays are that NumPy essentially has sequences or tables indexed by column numbers or row numbers. So it's always 0 to n minus 1. On the other hand, pandas are like tables with dictionaries. So we want column names or row names. So this allows us to refer to names, positions in a table by their meaningful value rather than just by the arbitrary position. So it's just like having a dictionary versus a list. So you can import the package pandas as shown here. And for instance, we can take a sequence, in this case a tuple, and convert it to a series. When we do this, we implicitly get a series in which the positions are numbered, the elements are numbered by position, just like as they are in a normal array. However, if we take a dictionary and convert it into a series, then we get positions which are named. So here, for instance, we have four values: IBM, a date, a number 100, and number 102, and they correspond to the concepts name, date, shares, and price. So this is much more useful and easy to remember and manipulate than saying that position 2 is the shares position and position 1 is the date. We can also create these row names by providing an index to the series function rather than feeding a dictionary as shown here. Once we have a series like this, which has, for example, row positions named, then we can extract the value at a position by providing that position name. So for example, if we want the shares entry, we say what is f at shares and we get the value 90. Go back and see that shares is the second position, 0, 1, 2. On the other hand, we can also do it positionally. So we can say what is the value at position 0 and we get FB. We can also pick out values at different positions. It's like a slice, except we can take any combination of these things. So here notice that we give this combination as a nested list. We give a list of positions at which we want the values, and we get those corresponding positions in the series. A two-dimensional version of this is called a data frame. So here we provide a dictionary where the key values will turn out to be the column headings, and each of the values associated with the keys will be the rows in the corresponding column. So here we have four columns called name, date, shares, and price. Each column has three entries. These will be the three entries in that column. So we are supplying the table in a kind of column by column manner. So once we set up this data frame, this is how we visualize it. So we have four columns and the rows are now numbered 0, 1, 2. And each of these columns was provided by three values in the previous data frame definition. As in NumPy, we can operate on this as a unit. For instance, if we add a column like a dictionary, we can just provide a new key. And like in NumPy, if we assign a single value to this new column, it will get populated in all rows of that column. As we would expect, you can extract data from such a table by giving the column index. So if we ask for the values in the column shares, then we get a new series which has position 0, 1, 2 and the three entries in that column. We can also use this lock function to access a specific row and a specific column, so a single entry in the table. A common way to generate such a table is through a spreadsheet. We can export a spreadsheet in a CSV or a comma separated value file in which each row in the spreadsheet is a line of text in the file and the columns in that row are separated by some, typically a comma, some character separator. So here we read such a file and we can store it now as a data frame. Head is a function which exposes the first few rows in such a table. So here we can see rows 0 to 4. Here is another table that we read using the CSV file. And here we use the corresponding function tail, which gives us the last few rows. So this suggests to us that if the last row is numbered 49,999, there were 50,000 rows in this table which we just read in. Once we have a table in a data frame, we can start filtering it. For instance, if we have the previous table which has movie titles and years, and we want those titles which are after a particular year like 1985, then we can say give me in T the subset of rows in which the column entry for year is greater than 1985. We can also combine these conditions using Boolean operations. So here note that we use the ampersand for AND. So we say here give me all the titles whose year of creation was bigger than 1990 but smaller than 2000. So these are all the movies which were created in the 1990s. We can also sort these things. So for instance, if we say that the title should be Macbeth, we get a subset of rows which meet that criterion. Then we can say within this subset, I want them ordered by the value of year. So the sort values function sorts by the values of the given column name. So in this way, we can manipulate a table by extracting selectively rows and columns according to a criterion and then rearranging them according to some sorting criterion.